I'm making this video as a reflection of how our roller coaster project went last Friday. And I want to begin this reflection by just acknowledging the wonderful craftsmanship and effort that you all put into constructing these paper roller coasters. And it was really great for me watching you guys work so productively on these coasters over the duration of the period. And it looked like everybody was actually having a really good time. And I really appreciate that. There were, however, some issues with calculations, and that became apparent in the second half of the class. And I have to say that I began, when I launched this project last week with you guys, I really emphasized the construction of the roller coaster. And I did say the calculations that you're expected to do alongside your project are pretty simple. And the reason why I was saying that is because we've spent the last month learning how to do these types of energy calculations. Notice section 5.3 in our book. This is page 170. Here is a sample problem. Starting from rest, a child zooms down a frictionless slide from an initial height of 3 meters. What is her speed at the bottom of the slide? And that really, a child going down a slide is no different than a marble going down a roller coaster, a paper roller coaster. So we are meant to be able to do a problem like this with certain proficiency, and then understand that really the marble problem, the roller coaster problem, is the same problem. Here's our formative from that section that we did a couple of weeks ago. And the first problem that required calculation, there's that same child, well, a different child that has a different mass, going down a frictionless slide from a certain height, find the speed. And on our summative that we took, we had a child going down a slide, which was a little bit of a different scenario, a little more challenging, because this child was starting with a particular velocity, and then they went down the slide, and we were meant to find their final velocity at the bottom of the slide. But I just sort of point those out because one of the reasons why everyone, for the most part, did pretty well on this summative, and I thought that as a group we had a pretty good handle on conservation of energy calculations, and after last Friday I'm not sure that we do. So I am transitioning now into a little reminder about how we conserve mechanical energy and what that means. Right here, in the context of our roller coaster problem, what I'm saying with this relationship is that the mechanical energy at point A on my roller coaster, which for me is the very top of the coaster where I release the marble, has to equal the mechanical energy at point B, which has to equal the mechanical energy at point C, regardless of where I put those labels A, B, and C along my coaster. I expect that the energy, that is the mechanical energy of the marble, is constant throughout this process. It might take different forms, energy changes from one form to another, but overall the total energy is the same at every given point. And let's look more specifically at point A. The mechanical energy at point A is going to be equal to the gravitational potential energy of the marble at point A plus the kinetic energy of the marble at point A. And if somehow there was a spring involved in this system and I was launching the marble with a spring, I would have to add a third term for the potential energy stored in the spring. But we don't have that in this particular problem. There is no spring or elastic potential energy in our coasters. So on the next line, I'm saying the mechanical energy at point A is equal to mg, the height, the mass of the marble times g, the acceleration due to gravity, times the height of the marble at point A, plus the kinetic energy right there. That's the formula for kinetic energy. And it really depends on both the mass of the marble and the speed of the marble, which at point A is just 0. The moment that I release the marble, I'm not pushing it down the slide. I'm just placing it on the slide and letting go. So that greatly simplifies my equation. There it is. I can calculate the total energy, the mechanical energy at point A of this marble simply by calculating the potential energy at A, because that's the only kind of energy that the marble has at point A. And it's simple enough. I can measure the height with the ruler. I know what the acceleration due to gravity is, and I can measure the mass with this scale right here. And so you put all that together and you do an energy calculation. And actually, when I went around and looked at all of your work, 7 out of the 8 groups, I was able to decipher some potential energy calculation at the beginning of the roller coaster. And these are the results that I found. And I might expect different roller coasters and different marbles to have different potential energies. Maybe even by a factor of 2, right? One coaster, if it's twice as high as another, you would expect it to have twice as much potential energy at the beginning. But notice, if you look at the smallest number, this one here, which is really just about 1/100th if I round. It's like almost 1/100th. And then the biggest one is here, about 12. So this number, 12 joules, is over 1,000 times more than this number. Surely none of these coasters no one of these coasters has 1,000 times more energy to begin with than another. So clearly, and notice also that your calculations are distributed between all of these. They go from hundredths to tenths to 1 to 2 joules to like 10 to 12 joules. So there is a large range of calculations based really just on this same formula. This is a unit issue. And you need to make sure you understand how to use SI units in your calculation so that you end up with joules. That is the source of confusion here and what's causing these dramatic differences in potential energies. And just to continue the lesson here, once you have a potential energy that you're comfortable with, what you see here is that all of that energy is equal to the mechanical energy at point A. So not only have you calculated the potential energy at point A, but you've calculated the total mechanical energy at point A, which, as you can see, is equal to the mechanical energy at point B, which is equal to the mechanical energy at point C. So you know how much energy this marble has at every point on the coaster. It's just a matter of what fraction of it is potential energy and what fraction of it is kinetic energy. And that's part of what you're expected to calculate according to this rubric. Take a look. The very first thing we're doing is just calculating the gravitational potential energy at 3 different points. And that's easy enough if you can measure the mass and the height of the marble at those points. You use conservation of energy to calculate the kinetic energy at each of those points because you know what the total mechanical energy of the system is. And if you know what the kinetic energy is, then you can use that to calculate the velocity at any given point. So it's important to understand how to do these calculations and also to see that just because we're applying these calculations to a real thing in the real world that we built doesn't make the calculations any different than the ones that we did in the book or on our formatives and summatives. So there will be an opportunity for you to revise your project. And you're going to need to read my email closely and work with your partner to schedule the time that you're going to do that. And I will also add that it is also important that you communicate your calculations in a clear way, and don't put me in a position where I have to decipher what it is that you've written and make guesses about what it all means. So that is an important thing, not just here on this project, but generally when you're doing a formative or a summative. You've got to not just get an answer, but communicate your process and make sure that the reader of your work understands and can follow what it is that you've done.